and people. He is particularly interested in combining knowledge in civil engineering and other disciplines such as nanotechnology, computer vision, electrical engineering, and material science to convert traditional structures into more intelligent systems with a perception of structures and surrounding environment. Today, Professor Sun Peng will give a lecture for us. The topic is development and application of non-contact sensing solutions for built environment. Let's welcome his performance. Please, Sun Peng.
Okay, guys, can you see my slides?
Yes.
Okay, great. First of all, I would thank the host, the Beijing University of Civil Engineering and Architecture, together with ISPRS, for giving me this opportunity to give this lecture. Actually, let me firstly introduce myself. I'm a professor at the University of Central Florida in Orlando, United States. And the topic today is development and application of non-contact sensing solutions for built environment. Before I joined the UCF, actually I spent 3 years at the University of Michigan working as a postdoc researcher in smart cities and sensing systems. And prior to that, I spent 5 years at Rice University in Houston doing a PhD using single wall carbon nanotubes to invent a non-contact smart sensing pen for structures to measure the crack development and so on. Without further ado, let me talk about my topic. And there you go. As you know, like recently, smart city is kind of a hot topic, and together with resilient cities, right? This is also the name of this summer school. And usually a city can be divided in 3 different layers. The physical layer, including for example, the physical layer of buildings, infrastructures, and so on. And we also have a cyber layer of data. For example, we use sensors to collect different things from different objects. That is, there's a specific study called the Internet of Things, right? That connects the cyber layer. And we also have a social layer of people. How can we use different devices and sensors to our life to be safer, healthier, and better, right? While behind this big picture, sensors are the driving force to connect the 3 layers, and we use these 3 layers to make our city more resilient. While most of my study is about sensors development and sensor system development, as you may know, in our world, even like in this classroom, we are using Zoom to connect ourselves, right? We have different sensors on our smartphones. We have cameras, we have LiDAR, we have thermal sensor, and so on. Like, before I dive into the specific details of this lecture, I want to talk about my group and my lab. My lab is called Resilient Infrastructure Sensing and Evaluation Lab, in a short form, RISE Lab. And RISE Lab provides smart sensing solutions to smart city infrastructures, such as bridges, roads, power grids, landfill, and offer human sensing solution in built environment, so that further data analytics of the collect data could be used to provide guidelines to better maintain and use these smart city infrastructures and built environments. While this talk will be divided into several different topics, and my research directions include mainly 2 parts. The first one in non-contact human sensing. For example, I carried a study on human sensing in public open spaces by using computer vision, and I performed passenger sensing in public transportation system as well. But today, the focus of this talk will be on non-contact infrastructure sensing. And this specific topic will include two parts because of time limit. I will firstly talk about a UAV-based remote sensing, and later I will talk about deformation and displacement sensing in structures. While the outline of this presentation will be divided into several different parts. Firstly, I will talk about the ideas or the definition of infrastructure in smart cities. And later, I will have a brief introduction of the UAV and different sensors in my lab. Later, I will talk about 4 different case studies. For example, case number 1, I will talk about UAV-based water sensing. Case number 2, I will talk about UAV-based landfill surveying and monitoring. In the third case study, I will talk about structural sensing using different cameras. It is called multi-perspective sensing. In the end, I will talk about displacement measurement in shaking table experiments. Firstly, let me ask you one question. What is infrastructure? It seems to be a very broad and vague word. Actually, the more precise definition is that infrastructure is a set of fundamental facilities and systems serving a county or a city. And infrastructure can be composed of public and private physical structures. In general, the physical components of interrelated system providing communities and services essential to enable, sustain, and enhance social living conditions. For example, the examples of the infrastructure may include roads, railways, bridges, tunnels, water supply, sewage system, electrical grids, and telecommunications, as you can see on the figures at the bottom. Well, after we know the definition of infrastructure, I always have the feeling or the passion to serve as a sensing guy. For example, to use a sensor load in my lab to perform some of the studies, sensing studies. I have a UAV, industrial grade UAV, as you can see on the top left corner. I have a mid-sized UAV with a heavy payload of 3 kilograms, and it will allow 3 payload at the same time. And also it is equipped with RDK positioning system. I will talk about this system later. And it is equipped with a lidar, with stabilizer. A stabilizer is called a gimbal. So once you use a UAV to carry, for example, cameras on the sky, you have to make sure the camera is not vibrating, right? That is called a stabilizer. And we have different imaging system. For example, we have a dual RGB and a thermal imaging system. It has 2 cameras alongside with each other. If you can see my cursor, you can see this picture represents the thermal imaging. And I also have a multi-hazard gas sensor that is on top of the UAV, the white box that is showing on the bottom figure. And I also have ultra high resolution inspection camera with a sensor size of 45 megapixel. I also have a multispectrum image sensor, which can be used to record multispectrum images. And on the figure on the bottom right, you can see me and my student that is putting their UAV together before the flight. And let me talk about each of the sensors one by one quickly. Firstly, this is a kind of a high quality, high resolution inspection camera. And right now, the UAV is using this sensor. The drone is using this sensor to take images in different directions. Later, you will understand why we have to take images in different directions, while instead of like taking images just downward. And this technique is called a smart oblique capturing system. And this technique can actually greatly solve the computation time and the surveying time if we have to use images to reconstruct a 3D object. And talking about the application of this sensor, it could be used for topographic mapping. It can capture images that can meet 1/500 scale accuracy. And we can use this sensor for cadastral surveying, and is quickly to can be used to quickly generate the centimeter level accuracy 3D reality models. And we can also use this sensor for natural resource management. Later, I will use a case study to elaborate this idea. And the video on the bottom left shows actually the RDK system. It is called Real Kinetic Positioning System. And by using this system, we can make sure the UAV is staying floating in the sky with the accuracy of several centimeters. This might not be very important in some of the cities. For example, for cities that don't have a huge wind, but for cities who has wind, for example, in Beijing or in Orlando, Florida, we have to use this because we have to make sure those UAV can perform well in a windy condition. Next, let me show you the application of using the images that are collected from different locations, different posts. We can actually use the hundreds and thousands of images that is taken from different direction or different location to reconstruct a 3D shape. Here you can see a shape of a building has been reconstructed by using a handheld camera. And here, let me show you a quick example of the reconstructed 3D shape of UCF campus. While in the middle, we have the student union. By using the UAV flying on top of the student union for roughly 20 to 30 minutes, we collect 500 to 1,000 images. And then we stitch them together using some algorithm. The algorithm's name is called structure from motion. Later, I will talk about this. The bottom right, the figure on the left shows a Google image, while the figure on the right shows a 3D digital model from the images. Here in this slide, I want to show you a 3D model that is generated from the photogrammetry based on a flight on top of a forest. You can see if you zoom in to the ground, you can see some of the very small details. For example, the launch pad, the cases that we have, and different equipment, and so on. Later, I will talk about this project. We use this project to measure the creek locations that is hidden within a forest. And the second sensor we're gonna use is called LiDAR. I know a lot of people might be very familiar with this because like during summer school, you might heard about other professors talking about different sensors, right? LiDAR is a short name, while the full name of a LiDAR is called a Light Detection and Ranging System. Actually, NASA and NOAA in the United States have been using this sensor payload for quite a long time. They want to use this sensor usually to get their topology information on the land. They want to have a survey purpose, either mount this on a satellite or on an airplane. And you can see there are some examples. The bottom right figure shows an example of a LiDAR sense, the 3D model of a traffic system. And different color represent different height, actually. And each time when the UAV or airplane carry the LiDAR, they fly, and millions of beams, light beams, has been shot down onto the ground. And the data will be collected and be analyzed to see whether this data is coming from a concrete, or is it from a tree, or is it from a water and so on. So in this way, we can differentiate objects to objects. And the reason why we have to rely on LiDAR, that is a good question. You know, like although we have photogrammetry, as I described earlier, but sometimes there are not quite good illumination conditions. For example, the light is not that strong to irradiate some of the area. So by taking image in a dark environment, it's not possible, right? So instead, we use an active sensing method like LiDAR. Instead of just collecting light, we send out light and collect the bounced back light pulses. So in this way, we can eliminate the limitation from the illumination conditions and so on. That is one of the big plus for this method. And talking about LiDAR for research, actually in the market, there are actually usually two types of LiDAR. One is on land, mostly used on land. That is at the wavelengths around 700 to 900 nanometers. But that causes a problem when those red light LiDAR is used for surveying on top of water. Those light will transmit into water instead of be reflected. So meaning once you use LiDAR to survey water, the light will not be reflected. Instead, they will penetrate through. All the energy will be dissipated into water. So meaning you have no signal be collected. So that caused a problem. Later, people invented a bathymetric LiDAR. It is instead of using red light, while people use a green LiDAR, because the green light at the wavelengths of around 400 to 500 nanometers, actually they can penetrate into water, but without losing much energy. And once the green light hits the bottom of the river, for example, the river bank, it will be reflected into the water and then into the air. In the end, it will be collected by the LiDAR sensor. So in this way, we can get the signal from the river bottom. So in this way, we can capture the shape of the river instead of losing all the signals. Here, I want to show you a small video of a 3D model from LiDAR. Previously, I showed you a 3D model from photogrammetry, stitched images by using structure from motion algorithms. Here, different color represent the different intensity that is bounced back by the light signal. You can see a lot of details has been vividly revealed, and like that is a very usual application of LiDAR to have a kind of a land management or forest sensing and so on. Well, now after the background information and the introduction, let me step into the main part of this seminar. Actually, in the rest part, I will mainly talk about 4 different case studies. First one is drone-based water sensing or UAV-based water sensing. Well, right now, I'm in Florida. It is still morning here. There's a very few interesting facts about Florida. It is in the southern east corner of the United States, and it is one of the flat states in the United States. Usually, like in some other states, for example, in Colorado, in California, Alaska, you have some tall hills or tall mountains, or you can have some valleys, right? The topographic information is rich, meaning you have top point, you have low point, plus minus, you might have few thousand feet. But in Florida, we have flat topography. And it is the lowest average topography of any other state, all other states, 51 states in the United States. And the the ground level is almost the same as the sea level, with the highest at the Brinton Hill in the northwest corner of Florida. It only is 345 feet, roughly around 100 meters. That is very flat. It might be good. It's easy for traveling, but it might not be easy for us to do the surveying work because the topology information is not that rich. Once you use LiDAR, it might not be easy to detect the big change or the small changes, right? The small changes from hills to valley. So it will impose some difficulties if I have to use a UAV to survey a Florida area. And the second challenge is that in Florida, we have a lot of trees. We have a lot of forest. So meaning the trees will provide a dense canopy on top. Suppose you are flying a drone or flying an airplane on top of the forest. If the tree leaves is too thick, it might be very hard for you to use a LiDAR, to use a light to penetrate those canopies. Meaning you can only get information from the tree canopies, but you have little information about the ground, right? Which is covered by the trees. And the third challenge in Florida for surveying is we have a lot of springs. We have a lot of creeks. And usually alongside of the creeks, there will be a lot of trees growing on top of it. So make it even harder for us to know the precise size and shape of these creeks and rivers, right? So I was talking to my colleague in my department, and he's working in water resources. Actually, in front of us, we have 3 different platforms we can use. For example, we can have spaceborne LiDAR system, which is AKA is ICESat or JETA, which is launched 2 or 3 years ago by USA NASA. But since those satellites are very high above our Earth, right? And also the measurement of resolution is very, very low since it is far away. So the resolution, spatial resolution for those LiDAR, for this satellite-based LiDAR is only 25 meters by 25 meters. That is the most accurate LiDAR results you can get, right? That might not be enough. In Florida, we might have a creek at the size of width of 0.5 meters or 1 meters. There's no way you can measure them by using the LiDAR, satellite-based LiDAR system. While that leaves us to 2 other choices. One is airborne LiDAR, which is we can hire some pilot to drive an airplane to carry the LiDAR on top of the forest, do a scanning. But still, the spatial resolution from this method is roughly 1 meters by 1 meters. So for an object at the size of 1 meter by 1 meter, it will only show 1 dot in your mapping. That is not good enough. So the third option is UAV-based LiDAR. Since the drone can be flown very low above the ground, for example, 100 meters above the ground, we can have richer information by flying the UAV slowly on top of the forest. When I talk about slowly, I mean, it is compared to spaceborne LiDAR and airborne LiDAR. But actually, it can travel at the speed of 20 miles per hour. And if we use the UAV-based LiDAR to sense the creeks or streams, it can potentially provide you a resolution 0.1 meter by 0.1 meter. So I talked to my colleague, so we can do this by using my drone. So in order to demonstrate my study, I use a case study location, which is called a Triple N Ranch, which is located in Santa Claus City in Florida. And it is a wildlife management area. You can see on the figure on the right, the red bounding box represents the location of the study. And the solid blue line represents a perennial stream, which means it has water all throughout the year, including summer, winter, and spring, and so on, right? While the purple line represents the creeks or small rivers that do not contain water throughout the year. Maybe it contains water in summer, but during the dry seasons in winter, might be no water. There's the kind of difference. And these curves are drawn by USGS. And as you know, those lines are from satellite-based images. So I highly doubt the accuracy of the lines. So that gives us a reason why we perform the study, right? Next, in order to study this area, we plan 3 separate UAV flights. Each of the color represent each of the time of the flight. Each of the flight will cover like roughly 60 to 100 acres, 40 to 100 acres. And each of the flight will use roughly 27 to 48 minutes. You can see each of the bounding box we use a dense scanning mechanism to measure the catchment digital elevation model. The UAV is fly in a zigzag trajectory or meander trajectory, so potentially it can densely cover more area. And this is a flight. And later, now I'm going to show you the ground point classification. In the beginning of this seminar, I talked about, hey, once we send out the signal, send out the light and collect it, how can I know whether it's a light that is from a tree or it is from a ground, right? So we have to perform some of the data analysis, or sorry, once we have the raw data, LiDAR data, we firstly have to classify them based on either the color and based on their elevation. For example, tree canopy is kind of tall above the ground, while the ground points is at a lower, relatively low level. And we can rely on the color. For example, the tree leaves are green compared to the soil. Soil is kind of dark brown or dark color. Or we can rely on the light intensity. For example, once the light is reflected from a rigid surface like concrete, you might be able to retrieve 80% or 70% of the intensity, original intensity. But if you shoot a LiDAR onto a tree leaf, because it contains some moisture within leaves, you might only have 30% to 40% of energy bounced back. So based on different features, we fuse them together, we do a ground point classification, we can separate what are the points that is from the trees and what are the points that is from just the soil or the ground. Here, the case demonstrates well at the bottom. We can separate the interference of the tree canopies, because in the end we only focus on the land shapes to do some. So that's why we perform the survey. While the figure on the left shows the digital elevation model. After we clean out the tree data, we just use the soil data or ground data to get the digital elevation model. Actually, it's a model represent the elevations. The dark color represent the low point, while the lighter color relatively represent a higher points or higher location. Since in Florida, we have a flat land, here you can see the dark color and the bright color. The difference between the two is only 5 to 6 meters. It's not that too much. While the figure on the right shows a merged digital elevation model once we merge the 3 pieces together. You can see it's pretty cool, right? And this is just the first step. While the second step is to get the channel network, to extract the channel network from the digital elevation model. what we do right now is along the blue line, we use different intersects on top of the digital elevation model so that we can get the profile figure of the river at each of the intersect. For example, the figure on the bottom right, you can see the red curve represent the shape, the profile of the water bank. So you can see like, hey, if we draw a line on top, we can find the middle point of the river, right? This is one of the precise methods to get the channel network compared to satellites. And later we can use a new algorithm. It could be either elevation based, as I mentioned, or it could be data driven. For example, using some deep learning or image processing tools to get the channel network. Next, let me show you the final results. Actually, the figure on the right represent the red dots represent the GPS tracking results. I hired a student to work inside the creek, for example, for two hours from the upstream to the downstream to give a relative ground truth results. You can see the red dots are kind of away from the blue line. Since the blue line is generated by satellite-based image, while we can say the red dots are more precise, more close to the reality. While the black and white figure represent the digital elevation model from my study. You can see the dark color shows very good match to the red dot, which is ground truth solved in this study. And here I want to show a small video showing how to fly, what is the feeling flying UAV on the sky. You can see on this screen, the left side, it shows a camera feature, RGB. You can see different colors, while the figure on the right, the moving dots, are actually the data collected by LiDAR, UAV-based LiDAR. While the figure on the bottom left shows the trajectory or the route we programmed for the UAV to fly on top of the forest. The figure on now this shows a front view of the UAV flying roughly 200 feet, which is 70 or 60, like 150 feet. I mean, like 50 meters above the sky. Yeah. And now we are carrying out some study for the flight route plan, because once we fly the UAV on the sky, we have to make sure, hey, we have enough battery, right? Otherwise, you will face a danger. Once you run out of battery and your UAV is not back into the station, the UAV will just fall onto the forest, onto the river, right? For this type of UAV, it is usually at the cost of $27 to $47. There's a time when I was flying the UAV on top of the forest with my students. Actually, we have around 5% battery. I thought like we can manage it, like we can still push in the next 5 minutes. But actually on that day, it's a windy weather, right? The wind is large. I didn't take this into consideration. Instead, once the UAV is flying back after the mission, there's only 1% of battery. It forces itself to land. And unfortunately, it is landed on a piece of grasses instead of water. If it is landed on a water, for example, lake or creek, I can say like $40,000 is gone easily. Okay, this is our first study. Now let me talk about the second case study, the UAV-based landfill surveying. Before I start this section, do you know landfills? Do you know landfills? Maybe later I can look at the chat to see some of the Q&As. Actually, like in a city, landfill is a very important component in our cities. We consume every day. We live every day, right? We produce trashes. We produce bio waste every day. Like, for example, today you eat a pizza, you cannot finish the other half. And the pizza within the box is thrown into the trash can. And the trash can is deported into a waste landfill. It's called a municipal solid waste landfill. And this project is a collaboration with my colleague, Dr. Nick Chen in environmental engineering. As I know, like I have talked many times with him, so I know the different parts of the landfill. Previously, I saw landfill is just a landfill. It's more like a dirt hill, right? But no, it's not the case. Actually, it's similar to structures. You have to design it properly. Actually, number one is kind of the landfill liner, which is constructed by either concrete or some other strong materials, right? You created this bowl shape, and then you dump waste on top of it. And for each amount of, for example, 500 tons of waste, you have to use a roller machine to make them packed. So this is regarded with the landfill operations and management. They have many technical issues. For example, can we monitor the landfill volume? And can we monitor the weight density? That would be useful parameters for them to estimate how much more trash can be dumped into the landfill, right? And regarding other issues, they might have the landfill gas and temperature issue. You can have landfill emissions, meaning methane emission, right? You have to check whether there's some leaking spot on the landfill. If you have this, you have to do some remedy. You have to repair the landfill. And thirdly, you have to think about stormwater management. If you have a hurricane, if you have big rain, will the stormwater drainage system working fine, or will the water stay on top of the landfill? If it stays on top of the landfill, it can create the dead load or live loads on top of the landfill, which can potentially damage the landfill. And we also have to consider the landfill anomalies. Some, for example, leachate outflow, cover integrity, vegetation discolor, and so on. Here's an image showing different issues that is associated with the landfill operations and management. Well, after talking to my colleague, I was told that right now people are still using conventional landfill surveying method. For example, elevation survey. Some people held a tripod with different like equipment, so that either LiDAR or some other equipment to do the manual survey. It is very time consuming. For example, surface emission monitoring. Some people just use a handheld like methane sensor, walk on top of the landfill, check different hotspots, right? You can see like it's very time consuming. Usually this kind of surveying will take you like more than 3 to 5 days to complete. And I talked to the engineers in order to hire them to perform this quarterly based surface emission monitoring. Landfills have to spend like more than $5,000 each time. So you can see throughout the years, they are using like potentially for large landfill, you can have like thousands of dollars or tens of thousands of dollars devoted into this surveying and monitoring purposes. So I was talking to myself, is there any way we can help them by creating an automatic sensing device by using UAV, the drones in my lab? And the research objective is coming from the motivation that we do have a huge urgent need for a timely and economically efficient method for the spatial temporal monitoring of the landfill surface emission. For example, that is number one issue. And number two issue is the land cover issue. For example, is any leaking, there's any vegetation discolor. If there is, where is the location and how severe the cover issue could be? Do we have to ask a landfill manager to have some remedy? Those questions are driving my research. And as you can see, the figure on the bottom, from the left to the right side, here's a continuous flow of this project. Actually, I just get this project. The project will be studied in September, and we will be using UAV, and we incorporate some low-cost multi-gas sensor into the UAV system. Together, we will use LiDAR. We will also use infrared thermal imager to collect the thermal imaging in a non-contact way. The figure on the second figure on the left shows the in-field scanning and inspection by using the UAV on top of the landfill. We can potentially get a multi-modality of data. For example, you can have the methane emission or methane concentration, CH2, humidity, temperature, and we also can get a 3D shape of the landfill. So later we can use this information for our flight. I will talk about this later in the next few slides. In the end, we expect to generate a landfill emission prediction tool by using the collected data. And the benefit for the end users could be like the effectiveness of using this method for management, right? We try to save the time and money by using this method. And this project will be divided into 4 different tasks. Number 1 is sensor to UAV integration. Although we have different sensors, different like commercialized sensors for UAV, we still have to develop sensors that is uniquely developed for this purpose to measure the methane concentration. We can integrate it into a sensor board and then be cased into the box, and the data will be collected in field, either be saved into a SD card or be uploaded into the cloud. While beneath, there's an algorithm called a structure from motion. Actually, the mathematical formula is kind of a optimization problem to try to use the features, share the features collected from different images, and try to use the shared images, shared patterns to stitch a 3D model. And task number 2 is that we perform a in-field surface emission monitoring by using the sniffer or the kind of sensor that is equipped with the UAV. The top left figure shows a 3D model in a RGB color, while the top right figure shows the digital service model, meaning right now we do not separate the vegetations with the soil. We just measure the top surface. It has another application. And the bottom left figure shows the laser intensity from the LiDAR, while the bottom right figure shows a DSM, digital service model, with a contour line overlay on top with a 5-meter elevation difference. And usually this landfill is at the height of potentially 30 meters or 40 meters and so on. And these 2 figures shows, the left side shows the RGB point cloud that is collected from the LiDAR. We are fusing a color into a data points measured by LiDAR. So we use cameras together with LiDAR together. We fuse the data, 2 different data sets. While the figure on the right shows a point cloud after classification. After the algorithm, we use the LiDAR intensity, we use the elevation feature, and we use color feature to separate the trees or grasses or bushes on top of the landfill. So we can just get the information from the soil. And here's the same figure, how to use this method to do the ground point classification. We have a software for this. And next, after the data classification, we can separate and we can have a cleaner data by using the reflectance from soil. You can see the left figure shows a hill shade map of the 3D model, while the right figure shows a digital elevation model with elevation contour. And each of the elevation tour represent a line with an increment of 1 meter increase. It's pretty cool, right? And the task 3 is the emission estimation and spatial temporal analysis. And later we will have a map of the methane emission concentration. And how gonna use this for spatial temporal analysis is a very interesting question. But I don't want to dive into the very details to get you guys bored. Next, the last task is to improve the landfill emission model. That is more kind of a mathematical or physical driven model. I don't want to talk in detail because it's relatively hard to understand. And next, let me talk about the UAV route, right? Previously, I talked to you, the UAV consume energies, they use batteries. So we have to carefully plan a route that serve our purpose. We cannot blindly fly UAV cover the whole area without a priority or without a plan. And here, I want to show you how I use some of the software to design the UAV route planning. For example, in order to match well with the traditional SEM route, I just designed UAV to fly at the same pattern. You can see it is following the meander shape on top of the landfill. And on the sideways, some of you can see the slope. So it's not flat. So we have to control the elevation and then the speed for each of the spot that the UAVs want to measure. In order to make it more similar to the traditional method, later we want to compare apple to apple. When UAV is flying to one spot for data collection, it is designed to stay there for 10 seconds. For example, the UAV is moving to the next stop, and after a few seconds, it will stop there. For example, it's here. And at this time, the UAV is sucking air from the ground into the air sensor so that we can measure the air quality on top of the landfill. So there are a lot of control part in the UAV applications. It's not as easy as you may think. And next figure, I want to show you some of the videos I use a UAV on top of the landfill. You can see the UAV is flying around 3 meters above the landfill. And you can see Sina, my PhD student, he is not controlling the UAV. Everything is automatically programmed. He is just monitoring the UAV so that the UAV will not be attacked by the big birds. You can see there are a lot of vulture and eagle that is hovering around on top of the landfill. They are hunting for trashes, right? For the waste pizza, right? Those are trash for human, but they are the food for the animals. It's pretty interesting. And next, I want to show the emission monitoring by using mapping results. We can fly densely on top of the landfill so that we can collect the CH4, H2S, which is kind of older. Although nowadays the landfill is doing a really good job by reducing the smell, but still it is a trash shell, right? The smell is not pleasant. And next, I want to talk about another sensor. It's called a multispectrum sensor. Actually, instead of using a normal camera to collect the color in 3 different colors, RGB, green, red, green, blue. Instead of it was collecting 5 different channels. Usually, human eye can only perceive light in the wavelengths between 380 to 700 nanometers. So in this camera, we can have additional 2 channels that are beyond the human eye. So in this way, we can see squeeze more information about vegetation or on top of the landfill. And here's a first view of the camera of flying a UAV on top of the landfill. And actually this is landfill with ashes, and this is mulch area. Most people have bio waste or yard waste. They dump their waste here. It's a different story. And also we performed some study by using multispectrum imaging with soil moisture. And we perform we collect 13 soil samples on top of the landfill so that we want to find the correlation between the multispectrum imaging with soil moisture. Next, I want to move towards the structure sensing. I want to wrap up quickly. So hopefully I can finish everything within the next 20 minutes. And the motivation of structure monitoring is that each year we have some of the disasters happening, right? In the past few years, there's a bridge collapse in Florida during construction, and there's a building collapsed near Miami Beach. So that is a driven force for structure for health monitoring. I believe most of you guys are familiar with the term, especially for if you listen to Dr. Ai-Chun Lee's speech. He is an expert in structure health monitoring and structure control. And he was my master's degree study advisor. And if you are familiar with this idea, I don't want to spend more time talking about what is structure health monitoring. Basically, it is just using the structural responses to infer whether the structure is healthy or not. That's all. And in the realm of structure monitoring, we usually have to record or measure the displacement. For example, the figure on the right, we want to measure the dynamic response in the middle of the bridge. We can do it in a traditional way. We can measure by ruler, or we can measure by LVDT sensors. But right nowadays, with the development of cameras and computer vision, we can use cameras to do these purposes non-contactly. And the idea of a vision system is to mimic human eyes, right? One camera you can see as one human eye. And the object is a 3D object projected into your eyes, forming a 2D shape for each of the one eye. In order to perceive or to understand the 3D shape of object or how far away is the object, we have to use two eyes. So that is the idea of stereotype cameras. Instead, by using one camera to detect the location of an object or the shape of an object, we can use two cameras sideways, different orientation. You can get the 3D information easily. So I was thinking, this is my student's project, like my student Sina, PhD student Sina, and he is trying to use multiple camera to get the location of beams on top of the beam. You can see we attach Apron tag onto the beams. Apron tag is kind of a tag system you can usually see in a grocery market or supermarket that carries a unique ID. For example, some of the tags represent one, some of the tags represent two. They have different numbers. And also it can help your camera to detect the unique features on object. And this unique feature can be shareable to other cameras. And here we want to use, for example, 3 cameras to monitor a 4-point bending experiment. We are bending the concrete beam, and by the same time, we measure the surface short deformation of this beam. And the algorithm behind is called a bundle adjustment algorithms. Basically, we use the shared features and we minimize the sum of the errors between the observed 2D pixel values and measured 2D pixel values, observed and measured. And there are a little bit of mathematics behind. So in order to know more, you probably check my paper or some other's paper. It's called a bundle adjustment algorithm. And next slide is showing the experimental setup. We are crushing the beam in the middle, and we are using 5 different cameras to monitor the process throughout the time. And the camera is set at the speed of 10 frames per second. So meaning every 1 second we are taking 5 images. And you can see the figures on the left shows the figures before deformation or before loading, while the figures on the right shows the beams has been crushed. You can see the big crack is happening. And also you can see some dotted patterns on top of the beams. And those are the patterns we on purpose created. So my next student, Mustafa, can perform digital image correlation to measure the strength, the deformations on top of the beam. And next is an example I borrowed from my YouTube. It's kind of a video showing how you use a structure for motion. Actually, although by using multiple camera and by using one movable camera seems to be different, but the inside code or inside the algorithm is the same. It's called structure for motion. In the end, I want to talk about the last case study. We want to measure the displacement in a shaking table experiment. In the structural sensing part, in case study 3, although we measure the deformation of a beam, but it is called a causal static, right? Although it is moving, but the movement is so slow. But if we have to record a quick movement of a structure, either it is shaken by earthquake or it is shaken by wind. How can we measure that? I'm talking about how you use cameras to record those data. Before that, let me show you one image or one video about the structural vibration. Here, there's a very famous bridge in United States, and it was built on July 1st, 1940. It is called the Tacoma Narrows Bridge, and it is a suspended cable bridge built in 1940s, I think in the middle of the World War II. And at the time, everybody is happy. During the open day, you can see a lot of trees, a lot of trucks and a lot of people working on this. But in November, only 4 months afterwards, it collapsed. And here's a video to show you about the structural vibration. You can see the structure is vibrating drastically. It is real. It is not animation. Actually, like this is only newly built bridge is vibrating like this way. It is real at that time, and the engineers want to find a solution. And let me skip some of the part. You can see how large the vibration, the amplitude. You can see the cables is shaking. And in this video, there's a professor parked the car in the middle, and later he come back to the car to rescue his dog. And fortunately, like his dog has been rescued. You can see. After only like several minutes, the bridge collapsed. And this collapse is due to the fluttering and due to the wind. So that's why later there's another discipline within civil engineering is called wind engineering is booming. We want to design a bridge with the optimum cross-section area, so this disaster will not happen again. And similar to with the wind, we have to like talk about like earthquakes. Although in Florida we don't have any earthquakes, but like in California we have earthquakes. So this is part of my study, and my student Mohammed is working in this part, and he has designed a shaking table experiment using a RC frame, reinforced concrete frame. And there are some different parts, some of the details, some of the design details, and so on. And the method we use is combine the OpenSea's FEM simulation together with the real experiment by using cameras. And you can see on top of the frame, the figure on the left shows a traditional sensor displacement. We have different accelerometer for each of the floor, which is represented by gray rectangular or gray square, while the circle-like patterns represent strain gauge locations. In addition to that, we use 4 different LVDT sensors to measure the dynamic displacement on each of the floor. So while the figure in the middle shows the frames that is attached with APROTEC, we will use this artificial pattern to measure the displacement on top of the frame. Let's see the results. On top, in front of the shaking table experiment, we have 3 different cameras. Camera number 2, number 2, number 3, number 1, number 2, number 3. So they have a shared coverage. And in order to simulate that, we use a kind of excitation, earthquake excitation. And here are some of the data of the excitation waves. And the figure on the right shows the acceleration response spectrum in periods, or later you can convert it into a frequency domain. And in this study, I will just talk about one case, number 4, with an amplitude of 0.35 G. In total, we performed 9 experiments by using the same excitation wave, but we increase the amplitude of the excitation to see the development of damages on top of the structure. And my students spend almost, this is a sound of my student. I forgot to delete the sound. Yeah, but the flow chart is more like this way. The first step is always to use the camera to have a proper setup of the camera's lens and light. And second of all, we attach the artificial or natural patterns on top of the structure. The third step is to use template matching for displacement extraction. And number 4, we use the coordinate conversion and scale factor. If we know the camera parameters, we can know what is the exactly location of X, Y, Z in order coordinate system instead of in tensor coordinate system U and V. Okay, in the end, we have to do some data analysis, and later we will have an evaluation of using this camera method with the LVDT, which is traditional method. For example, here are some of the results. And from the top to right, from the top to the bottom, you have the LVDT results. Right now we think this is more or less like a ground truth. And second is a computer vision based method. And the last one is a displacement signal that is integrated from acceleration, because you know that the acceleration is double dot of the displacement. By using double integration, you can convert acceleration into displacement, right? The figures on the right shows that the comparison of 3 different methods. Actually, you can see the computer vision method matches well, especially for the glow pattern between the computer vision based method to the LVDT based method. And arrow, there are small arrow, and this arrow could contributing from the calibration arrow in LVDT or camera calibration arrow in computer vision method. And we have evaluated our method. The arrow for our method is only within 13 millimeters. We will still have to investigate more in this paper. And right now we are writing a conference paper, a journal paper on top of this. And this will be published soon. And after this, we use a different signal processing method to analyze the computer vision method and LVDT method. you can see the continuous wave transform of the two methods give you almost the same results, right? The vertical axis represents the frequency domain, while the x-axis represents the time in seconds. Now I have covered the 4 case studies in my research portfolio. And this time I won't have time to talk about non-contact human sensing, but maybe next time. For my research, I also performed some other studies, either related to structures or human. There's a study I performed when I was a PhD student. I spent 5 years developing a sensing coating. It's called a smart skin. I use single-wall carbon nanotubes and integrate it into a thin film at the thickness of 0.5 micrometers. And potentially we can use this sensor to measure the strand mapping on top of a building or structure surface. And the figures on the top right shows a comparison between my method in measuring strand, epsilon XX, to the FEM simulation results. You can see the patterns are almost the same. And my future research directions might be like in human to structure interaction, UAV-based applications, and human analysis, activity analysis, and so on. And looking forward to future collaboration with any of you. Like if you guys want to look for a PhD position or researcher position, please let me know. You can send emails to my website, to my email, or check my website to see some of the active researchers we are doing. And thank you very much. This is the end of this presentation. If you have any questions, please feel free to ask. Thank you.
Yeah, thank you so much for Dr. Sun. I think the lecture is interesting, cool, and even splendid on some different study cases of smart sensing solutions in built environment. Yeah, I think it's cutting edge, passionate, and impressive. Yeah, I think our participants surely have some questions. Everyone can use Q&A session to raise your question to Dr. Sun Peng. Yeah, okay. I noticed there are already 3 questions in Q&A sessions. Dr. Sun, have you noticed?
Yes. I'm reading right now. I have 3 Q&A. I will answer them one by one. First question is from Manikanda. Hope my pronunciation is okay. He asked, "Hey, professor, how do you overcome the image distortion when camera collected image in different directions away?" Yeah, that is a very good question, because once you use cameras, the distortion is coming from the lenses, right? Once you have based on the focal length, if you and based on the size, is near field or far from field. For this distortions, this can be solved by using a calibration board in front of the camera. You can check John's calibration method published in 2000, I think in 2000. That is one of the popular methods. By using this method, you can get the distortion coefficient. And later, once you have the distortion coefficient, you can use these parameters to rectify your image. So meaning your image collected will not be distorted by using this method. Hope I can answer your question. And the second question is from Samuel. And in addition to the factors considered, what about the geological features and structures of the landfill area? I'm trying to understand your question. Like, are you talking about what are other geological features? Yeah, if that is a case, like actually, let me go to the previous slide for the landfill. For a landfill, actually the landfill features are not too much unless there is the damage. For example, let me show you one of the figure in the previous slides. Let me show you. For example, here, the figure on the bottom left, right? This shows a heel shade map of the 3D model. For example, this area, potentially you can see there's a dent area on top of that. That is an interesting geological feature we have to pay attention to, because once you have a concave area on top of landfill, once it is raining, this area will trap water. Once it traps the water, it will bring additional weight or pressure on top of the landfill. So this is an interesting feature we have to pay attention to. And the other interesting feature we have to pay attention to might be sinkhole problem. It might be a problem somewhere else, but in Florida, we have the sinkhole problem, meaning that from the ground you have a big sinkhole, so the land will collapse, will be concaved into the soil. And this potentially can break the landfill structure, because the trash has been buried within soil, right? But if you have the sinkhole problem, that can cause the damage on the outer layer of the outer feet of the structure, making some methane issue. The gas will be emitted. This CH4 is not good for our environment. And my third question is still from Manny Kenda, is why UAV should fly over landfill with less height from the ground, Professor? Is there any advantage for that? If the height is more, it can cover a wide area. Actually, that is a very good question, but the answer is, once we choose to fly low to the ground, because we don't want to cover the larger area. Our purpose is to get richer information. If you fly, for example, compare 200 feet to 400 feet, although you cover a larger area by flying high, but if the speed of your UAV is the same, the point concentration for each of the square meters will be fewer, meaning you have less data for this unit area. I hope my answer can provide answers to your question. So we do this on purpose to increase the density of point cloud. So later we have a large data sets. And question number 4 is still from Samuel. Is it necessary to consider the geological features of the area? Yes, it is. I think it will be beneficial, but not be necessary, quite necessary. And regarding this topic, I might have to talk to my colleague, because he is a domain expert in the solid waste landfill industry. All right, let me see. I do have some people providing comments from the chat. Professor Huang, do I have to answer those questions as well, or just a Q&A?
Yeah, I think you just need to answer the question in Q&A.
Okay.
Yeah,
okay.
I think the time is tight. I think, yeah, next lecture is will beginning.
Okay.
So I think, yeah, if everybody have any question, I think you can send email to Dr. Sun Peng.
Yeah. I have additional questions from Heron and Manikanda. Like, if you have any questions, please send to my email. I think my email address has been provided on the program, right? This summer school program.
Yeah.
Okay, great.
Okay. No problem.
Thank you for your attention. Thank you.
Thank you, Dr. Sun.
Heron, you can send an email. Thank you. Bye-bye.
Okay, bye-bye.
Let me skip it. Okay.
Hello, Professor Zhao. Can you hear me? My cameras cannot. Oh, okay, it's okay.
Yeah, no problem.
Good morning, Professor Zhao. I can't hear you. Please open your microphone.
That is
Okay.
right.
Yeah,
Can you hear me now? Okay.
yeah. Good morning.
Good evening. Good to see you all. That's nice. Okay.
Yeah.
I'm very sorry to have kept you waiting so long time.
That is okay. I understand. You know, how much time do I have? I hopefully I not run too much time. Okay. Keep you guys on schedule. Okay.
Okay.
Okay. I'm very glad to see you again. How are you going?
Pretty good. Same here. Yeah. Mhm.
Welcome to join us again. Welcome.
Yeah. Thank you.
Before your lecture, please allow me to introduce about Professor Zhao for our students. It's okay. Good morning and good afternoon and good evening, everybody. Today's last lecture is from Professor Zhao. Professor Zhao is a professor and engineering alumni endowed chair of environmental engineering at Auburn University. Starting August 16, 2022, he will serve as a professor and the chair of Department of Civil Construction and Environmental Engineering at San Diego State University. Professor Zhao has served as PI or co-PI for 15 research projects, totaling $9 million. He and co-workers have published more than 220 SCI indexed journal papers, one textbook, 50 book chapters, and 250 other publications. In addition, he has delivered more than 135 invited or keynote presentation or lectures worldwide, and he has been granted 7 U.S. patents. His works has been cited 16,000 times with a high index of 16.4 according to the Google Scholar. He is included in both the Clarivate World's Top 1% scientists and the Stanford World's Top 1% scientists. So it's your time, Professor Zhao, please.
Okay. Thank you, Hao, for the wonderful introduction. And again, good morning, good evening, good day. Okay. It's a pleasure here to share some of our research here. And it's a different topic. You know, I saw a previous one about the camera, okay, imaging there. And my area is environmental engineering. I like to talk something about soil and groundwater remediation issues, okay? And I know that's a little bit hard topic for some of you, but you can always stop me anytime. And again, this work, of course, is done by graduate students and postdocs. I listed some of them here, but not all of them. Okay, those folks are now all professors in China or other universities. Okay, so anyway, development and application of surface modified nanomaterials for in situ immobilization metals and metalloids in soil and groundwater. So we're talking about metals, okay, metalloids, it's contaminants, okay. All right, let me see. It doesn't move anymore. Try it again. Okay, so here's Auburn University big picture, those little bird view here. Give you some idea of beautiful campus, a little bit hot in the summer. And it's our president's building. It's a very famous football stadium, okay? those who have visited Auburn, you should know Auburn University is the biggest, sports university. Okay, and you probably know this lady is Olympic gold medal for gymnastics. Okay, Auburn University, and some ranking here. Okay, and Tim Cook was Auburn graduate and Apple CEO there. Okay, I'll give you some idea. Okay. We are a little bit 1 hour and a half from Atlanta Airport. Okay, it's pretty convenient, airport. Atlanta Airport is the largest airport in the world. Okay, and as a house that I'm gonna move to San Diego State University next month, actually. Okay, so to again to serve as a department chair in the civil and environmental engineering department. Okay. My research focuses here 3 areas, okay, and first one is in situ degradation of organic contaminants in soil and groundwater using the stabilized nanoparticles, and this is also our first, probably is pioneer work in the world. Okay, our group initiated this stabilized zero valent ion nanoparticles and proposes kind of in situ technologies. Okay, and those are the folks here, my first generation students there, and they established this area very well. Okay, my second area is about a topic I'm talking about today, about in situ immobilization of heavy metals and metalloids in soil and groundwater, also using stabilized nanoparticles, but different mechanisms. Okay, those are students here who have contributed to this field. And third area is the one I'm working on now, or focusing on now. Okay, concentrate and destroy persistent organic pollutant like PFAS. You probably have heard of PFAS. Okay, polyethylene perfluorinated alkyl substance, PFAS, fluorinated compounds basically, using adsorptive photocatalysts. Okay, again, those are the folks who did this part of work. Okay, so anyway, all this work is done by students, postdocs, visiting scholars. Okay, they should deserve the biggest credits. Okay, and as I said, this is about our Google citation profile. And our work probably cited about 8 citations per day. Okay, it is considered one of the highly cited research group here. Okay, about the soil contamination by metals. Again, this is a worldwide problem. It has been here for a long time. Okay, and we got whatever surface contaminants with metals, metalloids. Metals like heavy metals. Metalloids like arsenate, chromate. That's called metalloids. Okay, and they can slowly leach into groundwater, absorbed by groundwater soil here. Okay, and slowly release to groundwater. So drinking water will be contaminated by these metals or metalloids. Okay, they're pretty toxic. Okay, and causing all kinds of issues. The issue is also, once released into soil and groundwater, the treatment or remediation cost is very high, very costly. Okay? It's not just for in China, everywhere it cannot afford this kind of remediation cost here. Okay? That's why we keep looking for new technologies to save some money. Okay? Types and forms of metals, metalloids, and also radionuclides. We did a lot of work as well. So metal cations like lead, cadmium, zinc, copper, those are typical heavy metals, okay? And also you have oxyanions. Those are not, like arsenate, chromate, selenate. Those are anions, not cations, okay? They're present as arsenic, oxanate, chromate, okay? Radionuclides, uranium, technetium, okay? Those are also present in groundwater, okay? And a lot of times they are present as mixtures. Okay, it can be all different, not just single metals, just mixture of this are called contaminants, sometimes together with organic matter. Okay. And sources or forms of speciation. And of course, some metals on the surface can be as a big bulk materials. Okay, let's separate the face there. And some dissolved metal cation or anions can be absorbed, precipitated inside the soil, in underground basically, and they slowly release. Okay, slowly release into groundwater over time. And those metals, not like organic matter can be degraded. Okay, but metals you cannot be degraded. Any inorganic chemicals cannot be degraded. Okay, cannot be eliminated. But it can be transformed, okay, to less toxic form, or less mobile forms. Okay, for example, chromium-6 can be transformed to chromium-3, and chromium-3 is less toxic and less mobile, less soluble, basically. Okay, solubility. Okay, chromate versus chromium-3. Uranium-6 can be transformed to uranium-4, and which is less toxic, less mobile. Okay, same thing for technetium. Okay, 7 to technetium-6, 4. Okay, it's also less toxic. Okay, so you can transform them using some certain chemical reaction. You can also absorb them. Okay, makes them less mobile. Okay, immobilize. That's why we're talking about immobilize them. Don't let them move. Basically, let them stay in soil. That's the concept. Okay. And traditional technologies to control metals in groundwater, those pump and treat. Basically, pump groundwater out of ground, then treat it and pump it back. Basically, okay. Containment means you have metals in soil. Basically, you contain that part of soil, building some walls or landfill, whatever. To restrict the flow of these metals. Okay, bioremediation is less efficient, less used for metals. Okay, bioremediation is good for organic matter more often. Okay, then one more frequently used technology is so-called permeable reactive barrier, PRBs. Okay. And PRB basically is build a reactive wall on the ground. Okay, then you basically water can pass, but the contaminants will be intercepted. Okay, so capture the contaminant, but let groundwater pass through. Excavation landfill basically is for shallow. If soil, pretty shallow surface soil, you just dig out the soil, put it into a landfill. That's basically most straightforward method, but it's also pretty costly. Okay, a lot of soil there. You landfill them. It's very costly. Okay. Then injection reactive solutions. Basically, you can, inject some solution into the ground, and basically to either have metals immobilized, form precipitates, or absorbed. Okay, these are technology we have been using so far. Okay. And for soil remediation goals and issues, basically, a lot of metals in soil, okay, are absorbed. Okay, they are in a solid phase, but over time they slowly leach into groundwater. Okay, then removal goal: do you want to remove all the contaminants in soil from soil, or you only need to remove the portion that's leachable by groundwater? Okay, that's basically called a risk-based regulation. Okay, so far, most regulations, okay, are based on total amount of metal. Okay, that is sometimes may waste some money there. Okay, because not all the metals absorbed are available. Available means can get into water. If they stay in soil, it doesn't matter. It doesn't affect groundwater. That's okay. Okay, so sometimes like 50%, more than 50% metals may never get out of soil. then you probably don't want to spend money removing this soil adsorbed portion, okay, the solid phase portion. So that's why we are now in China or other places, in the US also, they trying to meet regulatory leachability limits. It's kind of like the US use TCLP. This kind of leaching test using like acetic acid based kind of special solution there. And just mix with soil, see how much metal leach out the soil. If you can meet some certain number, then you're okay to landfill your soil, waste there. In China, they use, a standard, it's called nitric sulfuric acid method to leach, trying to leach this, okay? To see the soil is, okay or not, metals concentration there is acceptable or not, okay? So those are things. And however, some issues there, like long-term stability or remobilization of immobilized metals are largely unknown, okay? Because after remediation action, okay, usually, okay, you turn in your remediation, okay, you pass the panel review, and then, the sites still stay there. After 10 years, 20 years, what's going to happen? I don't know. Okay, you have to know one follows up. Okay, follow up this kind of things. So that's one issue there. Impact of soil, groundwater, biochemistry. So you may add something chemical, add some remediation agents into soil. How is this going to affect your local biogeochemistry? Microbial there and chemistry there. How are going to affect other metals, other contaminants? Okay, it's poorly understood. Okay. And people also have different views about mobilization versus immobilization. Okay, and sometimes immobilization may be bad, just wash soil, just to dissolve the soil, metals from soil, clean up soil. Okay. However, that's very costly. You use different chelating agent, acid-based wash soil. It's costly, and also it creates a lot of waste extractants. Okay, you need to be treated further. And immobilization means you can add some agent, keep the metal inside the soil in the solid phase. Don't let it leach. That's the immobilization. Okay. And oftentimes we add an alkaline agent like base, sodium hydroxide, magnesium hydroxide. Metal hydroxide usually is precipitates, so they can precipitate out. And hopefully they're going to stay in the solid phase. And another method is convert, as I said, leachable metal into less soluble phase, okay? Just like chromium-6 to chromium-3 is very commonly practiced, okay? From precipitation, mineralization, nucleation, crystallization, different mechanism make the soluble metals into insoluble metals, okay? And add particulate materials to enhance absorption. You can also add particles, nanoparticles into soil. So you can, these particles are specifically made to offer high adsorption capacity and affinity for the target metals, okay? And issues, if you use liquid, okay, you say liquid, inject liquid into ground, this liquid is gonna flow with groundwater. So that can cause leaching more issues, okay? And if you use solid particles, then solid large particles cannot be injected into ground because soil itself is a strong filter, okay? It's small particles will be removed. You cannot deliver, cannot transport, okay, in the subsurface, okay? Modes of soil remediation are in situ. Okay, in situ means don't touch the soil. Just basically you deliver your chemicals or passivation agent into the source, soil in situ. Acid-based stabilized nanoparticles. That's the work we have done in my group. Okay, and again, the solution leaching is the issue here. Okay, and the particles you have to be deliverable, mobile in soil. And recently, for surface soil, we do on-site remediation. That means you can dig soil, mix soil, but don't move soil out of the site. Okay, that's in some Chinese factories, they don't allow you to move soil out of the the site there. So you can mix soil, and you can add a chemical, add particles there, but don't just do it on site basically. Okay, mostly for surface soil, and you need some heavy equipment to mix soil, to add your material, okay, mix with soil there. Okay. Off-site or off-situ there, basically soil can be digged out, either landfill it or dispose it somewhere else. Okay, but this one now is increasingly subject to regulations. Okay, and not like old days, people can just transport soil out of to some remote area. Not allowed anymore in many countries. Okay. Application of stabilized nanoparticle. Let's see just how this one works. So this metals, as I said, either absorb soil or you have precipitating soil, but over time, you can leach into groundwater. Okay, it's a long time process, a very slow process. So the idea is you inject this, for example, this is zero valent ion suspension here. The particles inject nanoparticle into the ground. You're gonna enhance the metal absorption, or you can transform the metal from soluble form to less soluble form, form more precipitates, okay, or form more crystals, okay. So those one will less leaching, or less metal will be leached into groundwater. That's the basically immobilization concept, okay. And alternatively, you can also build a permeable reactive wall. Traditionally you have dig up soil, then add your material, but with nanoparticles, because nanoparticle can be transportable inside the soil, you can basically directly inject nanoparticle to this soil zone here to form a reactive zone here. So groundwater can pass through the soil wall here, while the metals will be absorbed or intercepted, by other mechanisms. Okay, so that's two different uses here. And some requirement here again, nanoparticle must be deliverable. I use the word several times. Disposable means particle have to be. You can't spread. You have to be able to add the particles to the ground. Okay, they have to be able to move. Okay. Must offer high reactivity or absorption capacity. So these particles can react with the metals or interact with metals, so the metals can be captured. Okay. And particles deliver after once you get in soil, they should not spread out naturally. Okay. Basically, once delivered under pressure, whatever reason, then they still stay there, bound with soil, serve as a long-term sink, okay, long-term absorbent or sink there. Must not cause any significant adverse effects with this nanoparticle material. Whatever you add there should not, first, not toxic, okay? Second, should not mobilize other contaminants, okay? They are different contaminants, okay? And should not change the local biochemistry. Okay, those are things you need to be careful. So why nanoparticle? Nanoparticle has very high specific surface area, and they are very small size. Because very small, they can be delivered to soil. Okay, and they can actively attack this contaminants. Okay, and of course the challenge here is how to control the particle size. Nanoparticles are not stable in water. That means they are not going to be separate particles. Okay, once you prepare nanoparticles, they're going to aggregate. If large enough, they're going to aggregate into larger particles. If too small, they're going to dissolve. Okay, so nanoparticle, nanoscale particle themselves not very stable. So you have to prevent the aggregation, okay? And also injecting large volume water into ground, okay? If you have a lot of slurry there, inject this into ground, it can create some issues there. Uncertain interactions with soil and sediments, and some nanomaterial we don't know, how they're gonna interact with soil, biota, bacteria, okay? Cause what effect, long-term effect of this material, long-term fate and transport need to be investigated, okay? Environmental impacts, and also from lab data to field data, it also has a long way to go, from your experimental results. And problems with conventional nanoparticles is aggregation. Okay, you can see this commercial zero valent ion nanoparticle, they call it a nanoparticle, but they form large flux due to aggregation. Okay, and actually this flux even cannot get into the sand. It's a sand bottle here, column here. It's hard, it cannot really inject into soil. Okay. So that's why we start this idea called stabilization of nanoparticles, okay, trying to control the particle size, okay, prevent aggregation. And also passivate the surface, control the size. The particle can be transportable in soil. The theoretical mechanism is very, very simple. The classic electrostatic stabilization. You can coat a nanoparticle with a negatively charged, usually organic molecules here, okay, macro molecule. And the macromolecule here, you make the surface negatively charged, then they're gonna repel each other. So the two particles will not aggregate, not combine, okay? Another way is the steric stabilization, okay? Means this polymer molecules, if not charged, that's okay too. You'll have osmotic pressure. Once you coat the particle, they are not going to combine either. They're gonna repel each other either because of the osmotic pressure effect, okay? In our lab, we started this using polysaccharide like starch, carboxymethylcellulose, CMC. Is most they made our group most famous. We use CMC, okay, to stabilize different nanoparticles. And also new products called carboxymethyl starch. So starch is non-charged. Carboxymethyl, this one's negatively charged, okay, but this one's in the between. It's charged, but not that much strongly charged, okay. And also we synthesize nanoparticles in the presence of the stabilizer, okay, not it's not particles after they aggregate, it's harder to stabilize, but just because we just add this stabilizer before nanoparticles are formed, okay, they're basically more efficient, okay. And we can use different molecular size, different stabilizer to control the particle size, okay. So those are students who did this part of work. Starch and cellulose as a stabilizer is very cheap, and these are food grade, it's non-toxic, okay. We eat this like potato starch and corn starch, okay. It's very commonly used, food product. Now, starch is basically, you can see the molecular structure. So, a polymerized glucose. Each unit is glucose, okay? And they connect in different way here. And the amylose, that is called aminopectin. You can see the molecular weight change a lot, okay? 220K, up to 2 million glucose, okay? And as I said, this is not very water soluble. And some modified one can make it water soluble, and they can help you stabilize nanoparticles, okay? Sodium carboxymethyl cellulose CMC, and it's also very similar, still glucose here, but the functionalized glucose, you can see has a functional group. There's a carboxymethyl group here, okay? There's also carboxymethyl minus sign here. So that makes this molecule charged. So if you coat this molecule on the nanoparticle, nanoparticle surface is going to be negatively charged, okay? And that's going to help you stabilize particles to prevent aggregation, okay? So you can imagine this material, CMC compared to starch, starch no charge, okay? All those structures similar. CMC is charged. You can imagine CMC going to be work better because negative charge with negative charge particle repel each other. They cannot combine, okay? And as I said, this on CMS in between CMC and starch, okay? And still have same structure, but this kind of density of functional groups relatively lower, okay? Not as much negative charge carry, okay? That's another material can be considered. And this is how we prepare a zero valence ion nanoparticle with CMC here. So CMC solution, iron 2 here, ferrous ion, they form soluble complex. Then you add this strong reducing agent called borohydride, reduce iron 2 to iron 0. At the same time, you can see nanoparticles are formed, same time stabilized molecules are wrapped. Once the stabilized particles are coated here, these two ions will never get together. They cannot get together. If you do not have this coating, this 3 ion, the particle are going to combine into one larger particle, okay? That's how we call that stabilization, okay? And yes, our peers, call us, we are the first to get ZVI dressed, okay, get them dressed. And you can see the difference between non-stabilized particles, the aggregate here, and the stabilized particles. You can see the separate particles here. And if you put in water, you can see they are suspension, and these are precipitates. Okay, this large particle settle down. Stabilized one, you can see this kind of, it's like ink. You can easily inject this into soil. Okay. We tried to test this through a sandy column. You can see just pour this suspension through a column. You can see all can easily pass. And you can see this is tracer, bromide, 100% pass, and the zero valence ion, about 90% can pass the sand. Okay, they basically 10% will be retained by the column. Okay. And we tried this for chromium, trying to reduce chromium 6 to chromium 3. Okay, we did a column test basically. You can see here, without treatment, basically all chromium will be leached out, okay, by water. But if you add the, this, you pass the zero valence ions through here, basically you can see chromium 6 here disappeared. Everything is immobilized in the soil in the column there. Okay, so it's very, very effective. And this ZVI technology, we actually all the way from lab to the field. It's one of the field tests in California and Alabama. And we prepare nanoparticle on site because ZVI is very reactive. And if you stay too long, you're going to lose reactivity. Okay. And this is basically very easy. You have an injection well, then you have 3 monitoring wells, upstream, 2 downstream wells. So inject nanoparticle here, you can basically see what happens. So this is for chlorinated hydrocarbon, okay, chlorinated hydrocarbon, TCE, or TCE here, okay. And we're trying to dechlorinate the solvents. And that's what happened. You can see after ZVI injection, you'll see the reduction potential. You guys study water chemistry, okay? And it's very negative. -200 MV means very reduced in the environment, okay? And the chlorinated compounds can be reduced. And you can see here after injection in the monitoring well, you can see the TCE, PCE, PCB here concentration dropped by almost 90%. Okay. And there are some limitations, of course, with stabilized ZVI, rapid loss reactivity, side reactions with water, And surface soil is hard to inject. DOM inhibition, relatively high cost, okay, for ZVI, okay. And what's going on is that, let's see, slide show here. Do not want to do automatic show here. All right, again. And then in recent years, people try to use sulfidate the ZVI nanoparticle, basically combine zero valent ion and sulfide here, okay? So they have greater reactivity. Those are reducing agent, okay? Both are reducing agent. And so suppress ZVI corrosion reaction with water, okay? Basically, you can increase the electron efficiency, utilization efficiency, extend the reactive life ZVI. As I said, ZVI can lose reactivity very quickly. So you combine with sulfide, you can make it, more reactive and last longer. Okay. And the sulfide also offers additional reducing power, more resistant to DOM effect and pH effect. And how to prepare sulfidate ZVI, okay? And the traditional way is reduce iron 3 with borohydride and dithionite. Both are, dithionite is a reducing agent containing sulfur, okay? And you can automatically form iron sulfide mixture. It's one method. Another method is borohydride reduce ZVI. You form ZVI first and add sodium sulfide. So sodium sulfide reacts with ZVI, then form the core shell structure, okay? Core ZVI, shell is iron sulfide, okay? And our method is a little bit different. My method is very simple. I reduced iron to 50% or, whatever percentage to ZVI first, then add additional iron sulfide to precipitate remaining iron to as a shell here. You can form a shell, core shell structure also, okay? Very straightforward method. You can control how much shell you want to have, how much core ZVI you want to have by adjusting the, borohydride addition there. You can see here reactivity comparison. And so after adding sulfide, you can see iron sulfide shell here. The reactivity stay very, very strong, just like the fresh one. After 2 days, okay, 7 days reduce a little bit. After 21 days, still reactive. But if you do not add sulfide here, you can see reactivity decrease. Fresh 1 day, 2 day, 7 days. This high, you lose a lot of reactivity. This is a concentration of uranium, okay. And this 21 days almost no reactivity anymore. Okay, basically it helps you extend the reactivity there. Okay, I'll skip this one. And this is from Professor Feng He, one of my earliest students. He's now in Yangtze University, professor there. And he invented this method, basically started the phase reaction. He directly used ZVI, just grind the ZVI and sulfur elements using the ball milling machine there, okay? Ball mill them, basically, you're gonna form a ZVI sulfide structure here. And this one's very reactive, his material, and also easy to make. Okay? He can produce a lot. He got bulk products here, okay? And again, ball milling solid phase, powder there. And he also invented this theory, okay? So this is ZVI core here, and this is iron sulfide. The brown one here is iron oxide, okay? Some iron will be corroded. And he found that this iron sulfide part here is very reactive because iron sulfide is better electron conductor than iron oxide. So basically this point here, electrons here can be used to dechlorinate TCE. And this part here, basically by corrosion, you can release hydrogen here. So hydrogen here less reactive considered, but this part is really reactive. Okay. And here's double point or dual point theory. Now it's being widely accepted. 72% actual electron goes this way, can be used. Okay, 28% electron of through this way, less reactive way. But you can see the highly reactive point here, 72%, and that makes the electron utility much higher. Okay. According to his calculation or measurement, basically, his material can be, 1,000 times more reactive, faster to degrade TCE, okay, than ZVI, than the bare ZVI. Okay. So, little summarize about this: how stabilized can affect particle interactions. Okay. So, if you don't modify surface, don't use any stabilizer, nanoparticle and aggregate into larger flux. If you have a small amount of bridge there, I call it bridged nanoparticles, and a small amount of stabilizer, you form bridged one. If you have high concentration of stabilizer, actually you're gonna form the stabilized separate, discrete nanoparticles. Okay, and each of these material have their use. Okay, it depends on what you're gonna use for. Okay. And to inject to soil, this must be stabilized nanoparticles. For water treatment, you probably use the bridged one. The bridged one has the advantage of nanomaterial, still high surface area, but they can precipitate. They can settle down as a flux. And the bare one here sometimes more useful for soil treatment. Okay, if you want to treat surface soil, this one may be okay and still have high reactivity. Just show you how concentration of a stabilizer can affect particle settability. You can see here. No stabilizer, this is for magnetite nanoparticle. Without any stabilizer, this can aggregate to precipitate. You add a little bit, you can see the bridged one. This is a bridged particle, as I showed you. You form flux here, they can settle, but still nanoparticle. But the concentration to a higher, you can see they fully stabilized. And this is basically a suspension you can inject into soil. Okay. The surface coating can also affect the zeta potential, the surface charge. Okay. As I said, the CMC is negatively charged. If you coat CMC on the material, it's magnetite nanoparticle, you can see it's highly negatively charged. But if you coat a starch has no charge, neutral. You can see the surface become neutral charge, neutral potential. And if it's a bare particle, it goes from positive to negative, depends on what pH you have. Okay, high pH become negative surface, low pH become positive surface. Okay, those are things you can see. And starch concentration also can affect adsorption capacity for arsenic, for example, arsenic 5. And you can see the bare particle, very low affinity. You increase starch, you can see the particle becomes smaller, high surface area. You get a higher adsorption capacity or uptake of arsenic here. But after a certain point, you further increase it, doesn't help anymore. Okay, so just reach a maximum here. And our lab also synthesized all kinds of nanoparticle. One of them I call iron manganese oxide nanoparticle for arsenic 3 and arsenic 5. So this nanoparticle can adsorb, can also oxidize, because you have also, this is a reaction here. You have a manganese dioxide form, you have also iron 3 form. So basically iron oxide here can adsorb arsenate, and manganese dioxide is oxidizing agent, can oxidize arsenic 3 to arsenic 5. Okay, so this is how we prepare this material. Can again, the same thing. We have a stabilizer there. You can form this highly stable nanoparticle there. It's on the TEM image here. Okay, again, this is highly fully suspended. This one precipitates. Okay, without nanoparticle, without stabilizer. This is stabilizer. Okay. And you can see this isotherm data for arsenic 3 and arsenic 5. And most materials not very effective for arsenic 3, but this one's very effective for arsenic 3 removal because of the manganese dioxide can oxidize iron 3 to arsenic 5 here, arsenic 3 to arsenic 5. Okay. And then we did this in situ column test here. This is arsenic 3 contaminated soil here. We just pass this FeMn, iron manganese dioxide, binary oxide particle here through the column, and want to see how much arsenic 3 will be immobilized, or how much arsenic 3 will come out of the column. Okay, and we analyze two portions here. One is total dissolved arsenic, total arsenic coming out, and also we filter the material nanoparticle. We'll see how much soluble arsenic will be eluted from the soil here. Here's the elution data, and you can see here, this is just with water. If you rinse the column, just pass groundwater through the column, you'll see a high peak here, arsenic leach out. This kind of arsenic is very toxic. And this is 40 some milligrams, that's too high, okay? Arsenic standard is 10 ppb, okay, drinking water. And however, if you use nanoparticle to leach it, okay, this is another peak here, still very high, okay? But the difference is that with nanoparticle, the arsenic 3 is bound with nanoparticle, no longer soluble. If you check soluble arsenic here, it's only 6%. And this, if you use groundwater, 100% soluble, okay? So 94% soluble arsenic was was reduced, basically convert to nanoparticle associated. Basically, arsenic now, soluble arsenic becomes nanoparticle adsorbed arsenic, okay? That means if soil can catch nanoparticle, then the arsenic 3 will stay in the nanoparticle, stay in soil without leaching into groundwater. Okay, that's his idea there. Okay, and also we had another, had some field test based on this technology, based on concept. I just show you one example: on-site immobilization arsenic and lead at a chemical site there in China. And this site here has both lead and arsenic, mostly arsenic 3. Okay, and it's a large area, 2031 900 square meter, and produce this titanium sulfuric acid. Okay, anyway, lead and arsenic was a big deal here, and we tried to pilot the test 2,000 cubic meter. Okay, to immobilize lead basically on site. That's a vertical profile, concentration profile of the lead and arsenic. It's a depth, okay, underground depth. And there's 4 different points, 4 sampling points. The blue ones for lead, because lead concentration and the surface is really high. This is for arsenic, the red one, the arsenic. And in all cases, you can see the top 0.1 meter has the highest concentration. Anything below 4 meter, actually it's okay, and they can meet this regulation requirements. Okay, but we have to remediate, up to 4 meter here soil here, immobilize lead and arsenic. Okay, and we tried different agents. Okay, basically, initially we tried to use FeMn because we know this material is going to work for arsenic very well. Okay, and however, we, in China, you cannot buy potassium permanganate, okay? And this is considered controlled chemical, okay? So then we have to go with a different way. So that's we just use iron oxide, manganese dioxide, and manganese hydroxide at ratio 1:3, 1:2, 3:2, okay? As a mass ratio here. We have to mix this powder, then add it to soil, okay, because we cannot prepare this suspension. And why we use these 3 things, we have a reason here. Manganese dioxide can oxidize arsenic 3 to arsenic 5. The arsenic 3 is poorly resorbable, but arsenic 5 can be resorbed. Okay? Then arsenate here can react with lead form precipitate. You can see KSP value is very low. Manganese hydroxide can control pH from acidic pH to alkaline pH. Okay, and magnesium arsenate also good precipitate, very low KSP value. And lead hydroxide can also precipitate. Okay, so you want to form precipitate or form adsorbed species there. So this arsenic or lead can be immobilized in the soil. So first we did lab test. We prepared powder. We also compare with lab prepared FEM particles and also some other products. Okay, want to try them. Basically, we lab test. We add 20 grams soil mixed with 0.6 gram of this one of the agent there. Okay, in the bottle. Then just mix them, keep it in water, add some water, mixture 40% water there, mix and seal for 24 hours. See, then check the leachability, the nitric sulfuric acid leachability, the Chinese method there. Okay, and then we found that results here. So this arsenic leachability, this is lead leachability. This regulatory limit here. This is for regulation limit here for the dashed line. You can see this material cannot work. The initial value is too high. They're going to exceed the limit too much, okay? For sampling points, okay? And the FEMN definitely works very well, okay? But again, because we cannot buy the manganese acid there, okay, permanganate there, we cannot use this one. And then we use this iron manganese magnesium mixture 1, mixture 2, and this is starch stabilizer. Okay, this tells us starch stabilizer, non-stabilized one, all gonna work, all can meet the standard. Okay, same here for lead here. Looks like FEM no problem. Also, there's a bare FEM magnesium 3 mixture works very well. So that's why we chose this one, okay, for the field test. Okay. There's a dosage effect. If you increase the dosage from 1%, 2%, 3%, I can get this 3% has very good effectiveness. Okay, that's why we chose 3% for both arsenic and lead. Same time, immobilize both chemicals there. And the pH effect, this original soil pH is very acidic, about pH below 5. Okay, if you add one of the the chemical, our powder there, you can see pH 1%, 2% material. pH can go to neutral pH, alkaline pH. Actually, that's very good pH for metals. Acidic pH is going to leach out metal, but this pH is very healthy for for immobilizing metals. And this is a field preparation. You just basically mix the 3 powder together. You add to the soil there. Okay. There's a field site here. You can see basically you mix the chemical, add the chemical here, mechanically mix them with the both dose here. Okay. And see, we have a picture, another video here. Not running. Yeah, anyway, just add a chemical in the surface, 4 meter deep soil, back forth mixing them, basically. That's the idea. Okay. Video is not working, unfortunately. Let me check this one.
Yeah, it doesn't work.
Anyway, that's okay. We can just show you how they mix the chemical with surface soil again. Okay. Then just after 24 hours, we check the sample to the leachability test. You can see all the sampling points, red is arsenic, green is lead, they all meet the standards, okay? It's a surface soil sites, it's a deep soil sample, okay? All can meet the standards. And then we keep following this, field site for 210 days, okay? The students there just keep following them. 1 day, 3 days, you can see over time, the leachability gets low and lower, means the metals are more and more stable, okay? For both lead and arsenic, okay? And of course, right away is keep monitoring, for years, 10 years, 20 years, what's gonna happen, hopefully gonna stay like that, okay? pH, again, very stable pH after 210 days, still neutral alkaline pH there, okay? Because of magnesium hydroxide added there. And the cost, we did a little, rough cost estimate. There's a material cost here, labor cost, equipment cost, altogether, basically, you can see chemical cost about 131 Chinese yuan per cubic meter soil. Other costs, if labor in China is cheaper, okay, and the US could be very high, okay. And but the total cost in China would be 175 yuan per cubic meter. And this is a very cheap price, very low price. Again, soil in China, in US, remediation, 1 cubic meter soil can cost several hundred US dollar, okay? Easily 500 US dollar, okay, easily 700, okay? So that's about it. I guess don't want to hold you for too late, especially our Chinese students. Okay, it's 10 o'clock there. So I'll be happy to address so many questions if you have. All right, floor is yours, Patrick and Hao.
Yeah, thank you very much for Professor Zhao Dongye's splendid and attractive lecture. If you have any question, please put down in the Q&A session and or in the message board. Yeah, I noticed one student put down his question in the message board.
Okay. You mean, okay, the
class 2, BUCEA, yeah.
Okay, class 2, C2, you're right, okay. Is it necessary to ensure nanoparticles equally distribute in soil? And how to do that? And up to now, is there any negative effects of those particles being reported? Very good question, okay. Yes, it is necessary to evenly distribute nanoparticles in soil, okay? And that's a very technical challenge, okay? A lot of times, that's why a lot of times, if you not evenly distributed particle, you can clog the soil, okay? That's why we need to use stabilized particles. That's actually one of our contributions. But even our stabilized nanoparticles, okay, sometimes cannot be evenly distributed, okay? Some challenge, depends on your soil property. So my soil must have very good water conductivity. If the clay soil will not work, okay, for sandy soil, loamy soil gonna work, okay? And how to do that again? Because you have to use stabilizer, okay? Make sure particle can easily flow in soil, then you can help you distribute it easily, more, easily. And any negative effect, yeah, depends on nanoparticles, okay? People have studied all kinds of nanoparticles, but for our nanoparticles, because we prepare particles, we make sure this particle will not be toxic, okay? But other industrial products like silver nanoparticle, copper nanoparticle, people have found they can cause toxic effects to bacteria, to biota, okay? So a lot of people study toxic effect nanoparticles, okay? They are different way. But for remediation purpose, our particles, those are, iron oxide, magnesium, manganese oxide, those are, we know they're not cause adverse effect, okay? But need to be careful, okay? A lot of time we have to get a permit before you're allowed to inject particles. Okay, good question. Okay. Any other questions?
Any other questions? We gave the final 30 seconds. Okay.
Okay. I know it's
Professor
pretty
Zhao,
late.
have you moved? Yeah. Have you moved to the new city, San Diego?
No, I'm still in Auburn. I move next month. Okay.
Okay.
August the 10 or so. Okay. Yeah.
How far about the San Diego from the
From
Auburn?
Auburn, 30 hours drive. 30 hours.
30 hours.
Very far away. Very far away.
Okay.
California. Yeah.
Thank you, Professor Zhao. Thank you again. The wonderful speech for us. I think it's a deep questions for some students because some of the questions is about the chemistry. Some
Yeah.
of our students is not a major.
Oh, okay. That'd be tough. That'd be tough. Yeah. Must be environmental. Graduate student or undergraduate student understand it better.
Yes.
But that's okay. Just gives you some general idea, okay, about soil groundwater remediation.
Okay.
I mentioned there have questions in our Q&A group.
Okay. Let me see. Online note. Do you play rugby? Well, I love rugby. I wish I could. Okay. Are you from India or Pakistan? I play ping pong, table tennis. Okay.
Okay. Okay.
Could you save the email, Professor Zhao? Could you save the email for our students if they have questions?
Yeah.
They can send the email to our professor.
Okay.
Yeah, I think
It's
all
my
our
Auburn
participants.
email. I'm gonna still keep using my Auburn email. Okay, but I'll
Okay.
let you all know my new email after I get there. Okay.
Okay.
But I'll use this for a while, for a long time. Okay. So.
Okay.
And
Okay.
also,
I will.
yeah, go ahead.
Yeah, I will transfer your email to our WeChat group and some emails who would like to raise questions and further communicate with you, Professor Zhao.
Yeah.
Yeah.
I'm also
very
looking
much.
for good graduate students. Okay. If you guys interested in graduate study, let me know. PhD students. Okay.
Okay. Thank
Okay.
you.
Thanks so much, Professor Zhao. Have
Thank you
a
all.
nice day.
Okay. Let's keep in touch through email.
Right.
And
okay. Sounds good.
hope you will have a colorful and more wonderful career in the new university, San Diego State University.
Thank you. Right.
Okay, bye-bye, Professor Zhao.
Okay,
Bye-bye.
see you all. Bye-bye.
Okay, see you later. Bye-bye.
See you later, and see you tomorrow, our students.
Okay, hello, every students, every participants. Tomorrow we will give 5 lectures in tomorrow's schedule. In the afternoon of the Beijing time, we will give 2 lectures, and in the evening of Beijing time, we will give 3 lectures. I think it's diverse and unique. I hope you can enjoy our lectures of our summer school, and see you tomorrow, 3 o'clock. 3 o'clock p.m. Beijing time. Bye-bye.
Bye-bye. See you
Thank
tomorrow.
you for the hard working. Bye-bye. Thank you for hard working of my colleague from the